For arbitrary trajectory, we can study the distance traveled by an object, s of t, as a function of time. In the case that the magnitude of the velocity or the magnitude of the acceleration are constants, we can write equivalent equations as the ones we already studied. So, if this is the displacement or the distance versus time, we would write s of t equal to s naught plus vt, and s of t equal to s naught plus v0t plus 1/2 of a t squared, where s is the displacement, v will be the velocity. In this case we have constant velocity, in this case we have constant acceleration, and the only difference is that instead of talking of x as one linear direction, we're talking about s, which could be an arbitrary trajectory, where this would be s sub 0, and that's the distance traveled delta s as s minus s sub 0. Here, s should measure the distance traveled, the amount of meters, even though the distance to the origin will be different to it. For example, this distance is different to this trajectory. So v is the magnitude of the velocity and a is the magnitude of the acceleration. One particular and interesting case of trajectory that is not a straight line is a circular trajectory. In the study of linear motion, the important concepts are displacement, delta x, velocity v, and acceleration a. Each of these concepts has its analog in rotational motion: angular displacement, delta theta, angular velocity, and angular acceleration. We measure the angle in radians, the angular velocity in radians per second, and the angular acceleration in radians per second squared. The radiant is essential to the understanding of these concepts. Recall that the distance s around a circle is given by 2 pi r, where r is the radius of the circle. So if this would be the distance traveled s, if we divide by r in both sides of this equation, we get that this quantity is dimensionless, because this is measured in meters and this is measured also in meters in distance. 2 pi corresponds to a displacement around a circle. A half a circle would be just pi, and a quarter of a circle would be pi over 2. So 2 pi corresponds to 360 degrees, pi corresponds to 180 degrees, and pi over 2 corresponds to 90 degrees. So we introduce the radian with the relationship that pi radians is 180 degrees. So that's a new unit of angle, and radians is in the SI unit, so that's the unit that we're going to be using when we're talking about angular displacement, which is just the angle travel from an object in a circular trajectory. From here, for example, to here, this would be just a displacement delta theta, where this would be theta sub 0, this is theta, and delta theta is final minus initial. We will consider positive direction to measure the angles as counterclockwise. And the angle theta subtended by an arc length s along a circle of radius s. So this would be the distance s and delta theta. That's what has traveled that object. We can relate the angular displacement with the projector on an x-axis. So that would be the initial distance, and that would be the final distance related with those two angles, though. When s is equal to r, then the angle is 1 radian. Generally, angular quantities in physics must be expressed in radians as just mentioned. Be sure to set your calculator to radian mode. When a rigid body rotates through a given angle, all parts of the body rotate through the same angle at the same time. We can set up a fixed reference line and assume that at time 0 the point P is on that reference line, and after a time delta t has elapsed, P has also advanced to a new position. In this interval, the line OP has moved through an angle theta with respect to the reference line. The angle theta, measured in radians, is called the angular position and is analogous to the linear position variable x. An object angular displacement is the difference of the final and initial angles, theta final and theta initial. Delta theta is just theta final minus theta initial. Once we have defined the angular displacement, we can define the angular velocity omega as delta theta divided by delta t, and we can calculate the limit when delta t goes to 0 of delta theta divided by delta t, and that is just the derivative of angle theta with respect to time. So that would be the angular velocity. In the same way, we can calculate the angular acceleration as the derivative of omega with respect to time, which is just the limit when delta t goes to 0 of delta omega divided by delta t. Angular acceleration, again, it's measured in radians divided by second squared, and omega is measured in radians divided by second.